Hi, we're going to talk about probability today. And go ahead and get Notebook 10 open. And if you need to pause the video, do so. What we're going to do is we're going to start with some basic rules of probability, and likely that will be review material for you. Okay, but we're going to go over what we need, and then we're going to discuss the difference between theoretical and empirical probabilities. Okay, so theoretical probabilities are when we calculate things by hand, like mathematicians calculate probabilities on, with pencil and paper. Empirical probabilities are when we use a simulation on a machine. Well, this is the perfect class to do empirical probabilities because we can do simulations in Python, and you'll see that we're going to use a new method, a new table method called dot sample. So here I am. I've opened Notebook 10 and run the initial cell. And we're talking about probability, and there's some notation that we want to quickly go over. And so when we're talking about an event E, its probability is capital P, little r, and then parentheses E. So the probability of E, this is how we're going to this is the notation for that. Okay, and then these are things you probably already know, but perhaps written in this notation, they're a little weird. The first one says that probabilities are between 0 and 1. And if we switch this to percentages, it's that every probability is between 0 and 100%. Despite what our coaches may have told us when we were in middle school, you cannot give 110%. All probabilities are between 0 and 100%. Or in decimal form, if we're using decimals, between 0 and 1. Okay? And the closer the probability is to the value 1, the more likely it is to occur. And if the probability actually equals 1, then E is virtually guaranteed. Okay, so it's probability, so theoretically it's really hard to have a probability of exactly 1. But if we have something really close to a probability of 1, then that outcome is virtually guaranteed. And also the same for 0. If we have a probability that's very close to 0, then the probability, then the event E is virtually impossible. Okay, so that makes sense. What does 0 and 1 mean in terms of probability? 0% chance of something happening, 100% chance of something happening, either virtually impossible or virtually guaranteed. Now, when we're talking about not E, we're talking about the event not occurring. So this is like the probability of rain is 30%. So what's the chance of not rain? Well, all we're saying here is it's 1 minus the probability of E. So if the probability of rain is 30%, the probability of not rain is 70%. 1 minus 0.3. Give us the 0.7. All right, so I assume that most of these points are review for you, and hopefully you're getting a chance to see the notation in action. And then let's just take a look at example 1. Suppose an unfair coin is weighted so that the probability of heads is 2/3. What's the probability of tails? I hope you thought to yourself immediately, oh, that will be 1/3, right? Sorry, I'm running out of room there. Again, just using this, the probability of not heads is 1 minus the probability of heads. And in our second example, we're doing the theoretical probabilities here. All right, suppose a fair 6-sided die is rolled. What's the probability of it showing either a 3 or 5? Well, there are 6 things it could show. And there are 2 things that we're concerned with. So the probability is 2 over 6. So there are 2 equally likely things out of the 6 equally likely things. So the probability of one of those things happening is 2/6, which we would reduce to 1/3. Okay, so that's theoretical probability, and that's about all we're going to do of that, although some probabilities can be calculated in Python quite easily. And now we're going to switch to looking at some distributions and some empirical probabilities. Okay, So now what we have is a table called die, which just has the faces 1 through 6. 1, 2, 3, 4, 5, 6. And then we're going to use this new method that I told you about. It's a table method called dot sample, and it has an input here, this 10, and it means we're going to draw 10 times from that table. Okay, so there are 6 things we can draw. They're all equally likely. And so let's see what we get. Let me shift enter. Okay, and when we do the sample look, we end up with multiple 4s and multiple 1s. There are 3 1s that I see, a couple of 2s, a couple of 4s, a couple of 3s, and no 6. Well, again, this is random. It's done random draws. By the way, if you do it again, it's random. So it re-randomizes, and now we have different outcomes. Now we have a couple of 6s, 3 6s, before we had 0. And again, this dot sample method is randomly selecting 10 things from the table. And so every time you run it, it'll be slightly different. And now they're going to look at this histogram of these 10 outcomes. Sorry. Let me get here where I can. Okay, so what are we looking at with this histogram? Now that I've got it here where we can talk about it. Okay, well, what we're showing is the probabilities in the table, right? Everything is equally likely. This is called the uniform distribution, when all the bars in the histogram are exactly the same height. When all the bars in the histogram have identical heights, that is a uniform distribution, okay? And we're seeing an example of it. So now this roll bins equals, okay, so what are we doing? We are tidying up the bins. Why? Well, this bar looks better. This histogram looks better when we use the bins equals roll bins for this histogram. Why? Well, because the intervals along the x-axis are neatened up, and we still are showing 1, 2, 3, 4, 5, 6, the faces of the die. And again, we almost always use bins in a histogram to make the result easier to see, easier to understand visually. Okay? And now we're rolling a sample and looking at the histogram of the sample. So why are things weird? Well, because again, we're drawing a random sample of 10, and we know that each of the 6 things was equally likely on each of the 10 draws, but we've drawn them. And it turned out that we drew some 6s and 2s, 3s, and 4s more often than the 1s and the 5s. And again, if I rerun it, my histogram will look a little different. It's a random draw, and the histogram is showing the result. Now this one, die.sample 1,000, so now it's doing 1,000 draws. And you can see that it does change a little bit each time. But we're seeing that the bars are close to the same height. Not exactly the same, but we're seeing that, right? We're seeing the uniform distribution appear. Is 1,000 enough? I don't know. We're going to try 10,000 right down here. So let's do that and see. Okay, and now we're starting to see a little better histogram emerge. That is almost completely flat, right? The bars are really close to showing that uniform distribution. Why? Because the sample size is big, okay? So that, when our sample size n gets bigger, when it increases, our accuracy increases. So that's basically why statistics works. In layman's terms, it's a law of large numbers. When we collect enough data, we can get really accurate results, theoretically. Okay. And now we're going to talk about a situation where we flip 10 fair coins and count the heads. And so let me show you what's going on with this. We're using another method. And you'll notice that it's in the scipy.stats bin, right? That's the package that it's in. Okay, and what is it doing? Let's just see. So binomial means that it's yes or no, right or wrong. Okay. So the 5 is the number of correct outcomes, right? So if we're asking if we get exactly 5 heads, okay, so 5 is the number of correct outcomes. 10 is the number of trials, right? So we're flipping the coin 10 times, or we're flipping 10 fair coins. Okay, so the number of trials is 10, and then 5.5, sorry, is the probability of success. So a coin flip, 50% chance of heads, 50% chance of tails. And when we put all of that together in the stats.binom function, and we get the probability. So the probability of getting exactly 5 heads out of 10 is about 24.6%, or 0.246. Okay. Well, that's interesting. So what's the probability that we get up to 5 heads, right? So we could have 1 or 2 or 3 or 4 or 5 or 0, right? So what are we doing? We're doing NPA range so that we get an array in here that's going to be what? 0, 1, 2, 3, 4, 5, right? So it's going to be everything up to and including the 5. And then the 10 is going to be our number of trials. And then our probability is 0.5. Now look, this outer function is a sum. So it's going to calculate those 6 probabilities and then sum them up, add them up. And what do we get? We get the probability of getting at most 5 heads is about 62.3%. Okay. What is the probability that we get at least 1 head? So this one's a little bit funky. You have to think about it. They do NPA range 1, 11, 1. Okay, so basically they have everything that could happen. We could have 1 success, 2 success, all the way up to 8 successes, 9 successes, 10 successes. The only thing they've ruled out is the 0. All right, so the probability that we get at least 1 head, well, they're calculating the probability here. They're summing up all of the probabilities of 1 through 10. Okay. So this isn't, or well, this is the probability that we get at least 1 head. Right, so there must be like a 0.1% chance of getting no heads. All right. And then a graph of the distribution. Okay, so we just did NPA range, so that gives me 0, 1, 2, 3, 4, 5 up through 10. And let's look at this histogram. And please notice that it is nicely bell-shaped. Okay, so when I look at the tops of the bars, right, and I'm trying to hit the middle, but of course my drawing is imperfect at best. I am getting a bell shape when I think about the top of these bars, okay? And this is the left tail, these smaller bars to the left and the smaller bars to the right. These are called the tails of the distribution. And here the tails look almost equal, so we're saying it's a symmetric bell shape. Sometimes we have skew to the right, which means that the tail on the right is much longer. Sometimes we have skew to the left, which means that the tail to the left is much longer. And we'll talk about what that means more later. Okay, so if you missed it, if we're going to use this stats.binom.pmf function, we need to enter 3 values. The first value we put in is the number of items that are correct, then the number of trials, and then the chance of success. Okay, so just reviewing that real quickly before we move on. So we have a lovely story about the first hypothesis test. So Ronald Fisher is the father of modern statistics, the godfather of statistics, Ron Fisher, and he had a colleague, Dr. Muriel Bristol, and she's over in his office. They're visiting about something. They have a meeting about some project that they're working on together, and he offers her some tea, and she declines because the tea has already been poured, and she says that if you add the milk after you add the tea, it doesn't taste as good as when you add the milk first and then add the tea to it. Now, I am not a tea drinker. I have no idea. I wouldn't put milk in tea. That's not how I drink tea. Um, I like sweet tea, you know, and but they're talking about a hot tea, a cup of brewed tea. Okay. And there is a little bit of science here. If you think about it, if the milk is in the cup, say a teaspoon of milk is in the cup already, and then you pour near boiling hot water, the milk is cold, but the milk warms more slowly. But if you take a teaspoon of milk and dump it into 6 or 7 ounces of hot, nearly boiling hot tea, the milk warms much more quickly when you add it last, and there's a slight curdling. So it's not a huge taste difference, but there is a little bit of a taste difference, and Dr. Bristol said she could tell. And Ron Fisher and his buddy are like, she can't tell the difference. I mean, they hadn't heard, they thought it was preposterous, but they decided to have a taste test to tell. And so they gave her 8 cups of tea, and 4 of them were where the tea was added first, and 4 of those cups were where the milk was added first. And they're like, okay, tell us which ones are which. And they said, you know, and Ron Fisher was thinking if she identifies 7 or more correctly, her claim would be established beyond question. And so we'll talk about this in just a second, but let's talk about these probabilities. That's the next thing in our notebook. Okay. So now remember what this stats binom is doing, right? This is 10 successes out of 10 trials at a coin flip chance, right? A 50-50 chance. So what they did was they said, hey, let's set up this idea of a null hypothesis. So our hypothesis is going to be that Dr. Bristol is guessing at random. So we can calculate the probability of her guessing at random, and then we can compare the probabilities to the data we observe when she actually tastes the coffee. Okay, so if you want, and this is why we're doing some more dice rolls, and I am going to, instead of the dice rolls, I am going to do it more specifically for the tea example. Okay, so I'm just going to copy this. Now this is for dice rolls. I'm going to do coin flips, right? So I want the probabilities to be 1/2. And let's see what happens. What's the probability of her getting 8 out of 8 trials correct if there's only if she's guessing at random? And the answer is, well, it would be 0.39%. So it's less than 0.4% chance of her getting all 8 correct. And we can do the same thing. We can take the sum of some things here, right? Well, what's the probability that she gets either 7 or 8? Well, let's think about how to do an MPA range to get just the numbers 7 and 8. Right? It'll start at 7, it'll count to 8, and then it'll stop 1 unit before 9. So the probability of getting 7 or 8 correct is about a 3.5% chance. And then what's the probability of getting 6 or more out of 8 of those correct? Oh, and that's only a 14, that's all the way up to a 14% chance. Okay. And this will help you understand Ron Fisher's idea. He said, well, if she gets 7 or more correct, why, we're going to consider that she is not guessing at random. Why? Well, if I get 7 or more correct, look, there's only a 3.5% chance that could happen. Okay, so Ron Fisher used this cutoff of 5%, and he's like, look, if it's less likely than 5% that she's guessing at random, we're going to throw away that hypothesis. Okay. So what happened? It turns out, let's see, sorry. I'm sorry, and I did these already on the in the Python chart. And remember that this one was more like 14% chance of happening if she's guessing at random, but the 7 or 8 correct were very, very unlikely to happen if she was guessing at random. And sorry, that's moving on. We'll talk about this in just a second. Let me go back and finish the story. The story goes that she got all 8 correct. Dr. Muriel Bristol, in fact, appeared to be able to taste the difference. That was the conclusion that Ron Fisher came to, because he discarded this idea that she was guessing at random. Because if she's guessing at random, there's like a 0.4% chance that she'd get them all right. He's like, just based on the probability, that's nearly impossible, right? That's a probability so close to zero that that outcome is virtually impossible. So he instead decided that, okay, now we have evidence that Dr. Bristol can actually taste the difference. All right. And that was the first hypothesis test. He reported that later he was walking somewhere, and on his way he thought about this and he realized that this is the perfect setup for hypothesis tests, which we will talk about starting a little bit in the next video, and then right after spring break we'll launch into that. Okay. So fun story there about the lady and the tea. And so we're going to finish the notebook, and we're going to talk about the normal distribution and z-scores and the empirical rule. But before we move on, let me just make one more point. Okay, so Ron Fisher decided in the lady tasting tea example that the cutoff he would use would be a probability of 0.05. All right. Well, it turns out that every single hypothesis test that we calculate in applied statistics spits out a p-value, spits out a probability. And we're still using this one. So there are different ways to set the level of significance, but quite often, and if you don't know any better, if you don't have any reason to set it differently, the standard way to set alpha is, or set the level of significance is to set it at 0.05. Okay? And it's not just because Ron Fisher did that. It's because that he did that in, right after World War I, in the 1920s. And so we've had 100 years, and in practice, it works. It tends to be a really good value. Now, there are some niche problems where we adjust that probability slightly, but usually when we calculate a p-value from a hypothesis test, and p is less than 0.05, there's less than a 5% probability of it happening, we say the result is significant. Okay, so in the lady tasting tea, we're going to say, yeah, we have significant evidence that she can actually taste the difference in the tea. Okay, and you can go through some of those other probabilities that are in the notebook. They were all done correctly. I just showed you the ones that specifically relate to the lady tasting tea example. All right, so now what do we have? We have a table called fives, and NPA range 21. What's that going to do? Well, that's going to start an array at 0, 1, 2, 3. It's going to go up to 20, right? And then PMF, it's going to create a histogram of those 20 things. Okay. And why is it creating a table with columns? Because we want a bar graph of fives, and we're going to need it to be a table, right? So we're using this empty table and then creating the columns to have this data in it so that we can visualize the outcome. Okay. And what are we seeing here? What are we looking for? Well, okay, we get a histogram. Is it bell-shaped? Yeah. It's not perfectly symmetric. It's got a little tiny bit of skew to the right, and it's fairly narrow. And that's going to have to do for that because again, the notebook goes into the lady tasting tea, and you'll see that um, there are some calculations of those probabilities, just like we talked about. And let's jump back up to the normal distribution. What is the normal distribution? Well, normal distribution just means bell-shaped. Okay. And if you recall, we have seen this notation before, but if you haven't, let me tell you now that when we use a capital N and then the parentheses mu comma sigma, we're saying this is a bell-shaped distribution with a mean of mu and a standard deviation of sigma. Okay, and the standard normal is capital N 0, 1, which means the mean is at 0 and it has a standard deviation of 1 unit. Okay, so let's see this in action. Okay, so what are we doing? We're just drawing the standard normal curve. So you can see the center of the bell is right at 0. It is nice and symmetric. And then 1 unit away from the center is where the standard deviation is. Okay? Sometimes the standard deviation isn't very easy to pick out visually. But now we're doing a distribution that is n 500, 100. Remember, the first number is the mean, so the 500 is dead center in the middle of this nice symmetric bell. And there's, here's one standard deviation is over here, and one standard deviation below the mean, one standard deviation above the mean. Okay, so we're just getting examples right now. And now, what are we doing? Okay. We're shading this where x is less than 400. Why? Well, it turns out that n, 500, 100 is it's the distribution of SAT scores. Okay, so there are different components, right? There's a math component, there's a verbal component, and I don't even want to talk about critical writing, but anyway. So each of the components is worth 800. Now the average on that component is going to be 500 with a standard deviation of 100. And here, what we're checking on is what's the probability that x is less than 400. So what's the probability that a random student, a student selected at random who's taking the test, and we ask them what their score is, and the answer is less than 400. Well, you can see all the possible answers that are considered successes, right, in this experiment. We're looking for people scoring under 400. Well, the area under the curve, the total area under the curve is 100%, and we're trying to calculate the area under the curve because if the area under the curve is like 12%, then that's the probability. That's the answer that we're looking for. Okay, so let's check this out. Okay, and then what are we doing here? Well, we're seeing what proportion of the students score below 400, and we do the stats norm CDF where we want 400 successes, and we want out of 500 trials. No, I'm sorry. We're now using CDF, sorry, not PMF. So this is the mean, and this is the standard deviation. What's the probability of getting 400? Okay, and so now we're just calculating this area, this red area, all right? So about 15.9% or about 16% of students score 400 or less, okay? And then what's the probability that a randomly selected test will have a score between 400 and 700? You'll notice that the code is in here for us. And if you look at the drawing, it is shading, right, between the 400, right? That's where the red starts on the left at 400, and it stops at 700 on the right. And we're calculating the percent of that bell that's shaded. What percentage of the area under the curve is shaded? And it turns out that about 82%, right? 81.859. is the exact percentage. So about 82% of the area under the curve is shaded red. So the probability that we get a randomly selected score falling between 4 and 700 is about 82%. And we use this to estimate probabilities. And we use this to, to be able to sample and take the average of the sample. Then the average of the sample is going to be our estimate for the average of the population. We'll talk more about that later. Okay. Then standard units. So we want to talk about z-scores. Sorry, and I covered up the z-score formula so you can't see it. My bad. So z-score, and what is this saying? It's saying to take your score x, subtract the mean mu, and divide by the standard deviation. And what does that tell us? Well, it tells us the distance away from the mean in standard deviations, right? So if your score is 1.5 standard deviations above the mean, you're going to get a positive 1.5. If you're 2 standard deviations below the mean, your z-score is going to be -2. So positive z-scores are going to be for scores that are above average. Negative z-scores are going to indicate scores that are below average. And then we also will talk about standard units when we do more applied statistics. And at the moment, what's the key thing to notice? Well, we can use the sample, right? So the sample mean is x bar and the sample standard deviation is abbreviated S sub x. So we can do basically the same thing as a z-score for our standard units, and you don't have to understand that right this second. Okay, so what's the question? The question is, well, we've got boy-girl twins, and they're both pretty tall. Richard, a male, 6'5", Rachel, a female, 6'1", and what they do is they say, hey, we can see who's more unusually tall based on their own distribution, because for males, we know that heights follow a distribution where 69 inches is the average and 3 inches is the standard deviation. So that's 5'9" with a standard deviation of 3 inches. And here, the average for females is 64,4, which is 5 foot 4 inches with a standard deviation of 4 inches. And so who is the most unusually tall? Well, we're not asking who's the tallest. I mean, Richard is 6'5", his sister's 6'1". They're both very tall, but Richard is taller. But who's tallest relative to their own group? Okay, and sorry, I was trying to hit Shift Enter and go down. Okay, so what are they doing here? Well, they're calculating this z-score. Okay, so for Rachel, we're taking her height in inches, 6'1", that's 73 inches, minus 64, which is the average height for females, divided by 4, which is the standard deviation for females. And that score, her z-score, comes out to be 2.67, or 2.666, repeating. We do the same thing for Richard. We take his score of 77, which is 6'5" converted into inches, right? 72 inches for 6 foot plus 5, so 77 inches minus the average, which is 69, minus the divided by the standard deviation, which is 3, and wait, got it, okay. And so his score, I'm sorry, I got them confused. Okay, so this is the one for Richard. Maybe I should type that in so you can see it. Wait, 73 minus 64, that's for Rachel. So let me just put a hashtag. And so when we calculate Rachel's z-score, we get 2.25, sorry. And this one is Richard's. I said that the wrong way around. Sorry. So Richard's z-score is 2.6666 repeating, and Rachel's z-score is 2.25. So we would say that relative to their biological sex, right? Relative to males, Richard is 2.67 standard deviations above average, and relative to females, Rachel is only 2.25 standard deviations above average. So Richard is more of an outlier. A more And he's just further away from the mean. We would say he's taller relative to his population than his sister is relative to hers. Okay. And so what are we doing here? We're showing the probabilities that we just calculated, right? And so the z-score for Rachel is way out here. And you can just see we've shaded everything above her height in the distribution. It's just this tiny little area of red. Okay, and what are we doing below it? We'll do it for Richard. And there's even a tinier bit of red that you can see for Richard. So again, that's why we use z-scores. Z-scores are very helpful to tell us how distinct an outlier someone is. So we tell distance using the standard deviation, and the z-score tells me the number of standard deviations I'm away from the mean. So the z-score is basically telling me how far away from the mean that my score is. Okay, and then we're going to look at a couple of graphs here. This graph shows in a normal distribution, these are the scores that are within one standard deviation, so 68%. And I'm zipping through. Why? Because we have the empirical rule laid out kind of nicely for us. And I'm sorry, it's just hard to get it all on the same page here so you can see it. But here it is. The empirical rule says that, hey, within one standard deviation of the mean, we're going to capture about 68% of all the people in that distribution. So we're talking about SAT scores. About 68% of SAT scores are going to be within one standard deviation of the mean. Okay. Within two standard deviations, we're going to capture, 95%, right? So if I go 2 standard deviations below and I shade up until I'm 2 standard deviations above, then I'm going to capture 95%. But within 3 standard deviations, I am going to capture almost all, right? 99.7%. Now, we have computers and we can calculate these percentages very, very accurately. But 100 years ago, when this was first invented, the empirical rule was a way for statisticians, data scientists to estimate what the percentages might be. Remember, they didn't have a calculator. They didn't have a computer. So a lot of these calculations were done by hand, and they could estimate them mentally using the empirical rule. Okay. Sorry. Just trying to go down from there. And sorry, let me get rid of these stray marks. So we talked about this level of significance, and you heard me say alpha. I shouldn't have, because we didn't talk about it yet. But what is alpha? Alpha is the level of significance, and when p is less than alpha, we say the result is significant. And on the slide, I showed comparing p to 0.05. Why? Because ever since the lady in the T, Ron Fisher, set the percentage, set the level of significance at 0.05, and it turns out to be a really good value to use. It's not the only value ever used, but it's certainly the most often used. And it's a good for an introductory statistics course, elementary statistics. It makes sense just to default to the one that works the most often. Okay? So, and why do we study probability and statistics? I did say this. Each hypothesis test that we conduct will calculate a p-value for us, which is a probability. And then we're going to compare this p-value to the level of significance, which is almost always 0.05. Right? And so that will set us up for what we need to start looking at hypothesis testing next.